All right, so yesterday we went over what happens when two waves try and occupy the same space at the same time. Okay, and that is that they interfere with each other. There's two kinds of interference, constructive and destructive. Okay, we looked at a couple of the types of problems that we might encounter for an interference problem. Okay, what we're going to look at today is similar. Now we're going to look at what happens when waves encounter a boundary. Okay, that is that they change from one medium to another, or a place where the properties of the medium they're traveling in start to change. Okay, why would waves behave differently if they're going from one medium to another? What might change about them if they're going from one medium to another? The speed might change. What else might change? Something else has to change when speed changes because something else can't change. Nope, period can't change because period and frequency are the same thing and frequency can't change. So what's the other thing that's in the universal wave equation along with speed and period? Wavelength. Okay, so the wavelength will change and the speed of the wave will change, and sometimes that even means the wave will change direction. It'll actually physically turn, okay, and change direction depending on what kind of interaction it's having with the particular boundary. So we're going to look at all of those kinds of things. The good news is there's not really a lot of problem solving or math to do with this particular concept, but a lot of diagram-based problems and questions. All right, so there's a lot of visually represented stuff in this lesson. Okay, so we got to learn what happens when a wave encounters a boundary between two media. Understand that while many characteristics of a wave change upon entering a new medium, frequency/period never changes. Okay, and learn what happens when the properties of a wave change. Okay, so waves can travel through lots of materials. Okay, some types of waves travel better through certain materials than others. All right, so for example, transverse waves, okay, travel better through lighter materials, whereas longitudinal waves, okay, compression waves like sound, travel better through more dense materials. Okay, just the nature of the types of waves. Okay, when light, which is a transverse wave, passes from one material to another, its speed actually changes. Okay, it can slow down. Most materials, well, actually all materials, slow light down. Okay, it travels fastest in a vacuum, but when it encounters another material, it will slow down. And that is why we see light bend when it goes into another medium. Okay, it changes direction. Okay, everybody with me there? In fact, this idea, it's called refraction, is crucial if you are cutting stones to use in jewelry. Right, so if you have a diamond, for example, right, and let's say that we're going to cut it. That's not very symmetrical, but you get the idea. Okay, so what you want to do with a diamond, you want it to sparkle, obviously. And the only way for a diamond to sparkle is if the light comes back out the top facet. Okay, each one of these sides is called a facet. All right, so you want the light to come out the top. You don't want it to go out the bottom. If it goes out the bottom, you don't see it up here. Everyone kind of follow there? So what you have to do is you have to cut the stone at a certain angle, depending on the material it's made out of. Okay, so for diamond slows light down a lot. Okay, like it's one of the slowest materials for light to travel through. So if I have light coming in, okay, I want it to hit the diamond and slow down. Okay, and then I want it to hit the bottom facet. And if I cut this at the right angle on the bottom, instead of going out the bottom, it'll actually reflect off the bottom. It'll hit this facet, reflect off of it, and then come back out one of the top faces. Okay, making the diamond appear to sparkle. Right? Diamonds don't sparkle as much underwater because there's not as much of a difference in speed between water and diamond as there is between air and diamond. Right? Now, it's crucial that you cut these stones at the right angle. If you've ever seen a raw diamond, it doesn't look all that special. Okay, a raw diamond that comes out of the ground just looks like kind of like quartz almost. It's kind of that clear rock. Right? But once you cut it, it sparkles and shines and it polishes up much nicer than anything else. For diamond, there's a certain angle for the bottom of the stone in order to make this happen. For a cubic zirconia, which is made out of a type of glass, that angle is different. That's what a jeweler looks for if they're trying to determine whether a diamond is real or fake. Okay, all they do is put on the little monocle thing, okay, and look through, and they look at this bottom angle. They can tell right away the angle is significantly different for something made out of cubic zircon than it is out of diamond, right? So guys, life lesson, don't cheap out, okay? It's really, really easy to find out if you've cheaped out, okay? If she's worth it, get the diamond, okay? If she's not worth it, don't marry her in the first place. That would be my suggestion, okay? She's not worth buying a diamond, real diamond for. Think about it, okay? If you buy the cubic zirconia, she'll find out, and you'll be in a lot of trouble. I don't speak from experience because I'm smarter than that, but some of my friends, yeah, not that smart. Didn't work out well for them. All right, so does everyone get the idea here? We change the speed, so we change the direction of travel. We also change the wavelength a little bit, but we don't change the frequency, which means if I shine red light into a diamond, it comes back out red, right? I'm not changing its frequency. Okay, it'll stay the same color. If I shine green light in, it has a certain frequency. It comes out green. Okay, it doesn't change that part of it. All right, same thing happens with, well, this is what it would look like if we could actually see the light waves, which are way too small to see, obviously. Okay, it would look like this. They would be coming in, and you can see that their wavelength is quite a bit longer out here in the air where they're traveling very fast. Okay, but what happens is part of the wave encounters the water before the other part, and it slows down. Okay, so it falls behind the rest of the wave, right? Eventually, the whole wave gets in there, and now the waves are considerably shorter, and their direction is slightly different, okay? In the same way that if I want to, like, if you're running past me and I grab your arm as you're running past, do you change the direction? I didn't grab all of you, I just grabbed one part of you, right? But I slowed down one side of you, and that caused you to turn, okay? The same is true for waves. If I slow down one part of the wave, I'm going to get the wave to turn. Okay, everybody all right with that idea there? Connor, question.
Wait, so colors have to do with frequency?
Colors have to do with wavelength and frequency, yes.
So then your eyes become other creatures come together colors.
Yes.
Your eyes also have like a certain frequency, like your ears.
Yeah, the cones, which are the color receiving cells, sense like within our eyeball, they're typically near the back. They can only detect certain wavelengths / frequencies of light. Okay, so what we call the visible spectrum is what we can detect, right? Bees can apparently see well into the UV part of the spectrum, right? So flowers look a lot different to them than they do to us, right? So lots of times like a white flower might look very different to a bee than it does to us because we don't see that it's also reflecting certain ultraviolet wavelengths that they can detect. So we only see the visible spectrum, right? That's a narrow range of frequencies of light. Okay, there's obviously much more than that, like X-rays are way beyond what we can see. Okay, gamma rays beyond what we can see. Heat waves, okay, we don't see that, right? We can see the effects of it, but we don't see them themselves, right? If I want to use night vision, okay, if I want to use like true FLIR, like the forward-looking infrared, like they have on the police helicopters, okay, that detects wavelengths that we can't see. Just they're too long. Okay, the frequencies are too short. Okay, for us to see that, right? So, but they can be detected by that camera. Thus, if you are running from the police helicopter, forget about it. Okay, they have forward-looking infrared. Even in the pitch black, you stand out like a sore thumb against the surrounding cool environment. Okay. You ever watched that on TV? Okay, when they're trying to run away and they've got the helicopter, okay, and they show you the forward-looking infrared. There's this like white, like gleaming white, glowing white person running along with a completely black background, and then you usually see the glowing white police dog. Then it gets funny after that. Okay, but yeah, okay. So I've seen ones where the guys are like hiding under trucks and stuff, and they think they're gonna, or in the bushes, but they just stand out plain as day. The guys in the helicopter just direct the police right to them. So, okay, that's a form of light, and we just can't detect it with our eyes, but we have sensors and things like that that can. Okay, so big thing to remember here is that waves can travel through lots of materials, but when they travel to another medium, their speed and wavelength will change, and that can change things like the direction and stuff like that of the wave. All right, so what I'm going to show you here is kind of what that looks like first. All right, We're going to look first at one-dimensional waves. Okay, one-dimensional waves have to do with basically like something traveling through a spring or a string, or probably when you were a kid and you had the garden hose out in the backyard and you do this and the wave would travel along the hose and you'd giggle and then you do it again and then you get bored. Okay, but you can certainly run a wave through kind of any material like that. So what we want to look at is what happens when the wave goes from one material to another. So if I've got a dense medium, okay, and then a less dense medium, the speed of the wave will change when it goes from one medium to the next. All right, so here's my incident pulse. Okay, we call it incident because it's the one that's coming in. Okay, so it's the incident pulse that's coming in. Okay, we want to kind of observe its wavelength a little bit here. All right, so that little green line there will represent its wavelength. When it gets to the boundary, two things will happen. Some of it will go through, and some of it will reflect. At any boundary, there's always some reflection and some transmission. Transmission means to go through. Okay, everyone okay with that idea? Okay, so some of it gets reflected, some of it goes through. What determines how much gets reflected is how different the two media are. Right? If I just hook two identical springs together, is there going to be any reflection at all when the wave goes from one to the next? If they're identical, no, because it's not really changing the medium. It's just going from one identical spring to the next. Okay? But if I hook a slinky onto a heavy spring, then I'm going to see a fair amount of change between the two, which is what I'm going to do here in just a minute. Okay? So in this case, I've got my incident pulse coming in, and then a little while later, I've got this pulse going through. That's my transmitted pulse because it went back. Okay? And I have this reflected pulse coming back off of there. Okay? So looking at this diagram, did this wave, when it got to this medium, did it speed up or slow down? It sped up. Okay, here's how we can tell. Remember that wavelength and speed have to do the same thing. If the wave gets longer, that means it's traveling faster. It gets longer because the front of the wave gets into the new medium before the back, right? So the front runs away from the back and it stretches. Okay? And we can clearly see that in the red medium here, the less dense medium, that wave is traveling more quickly because it's longer, right? The other way we can tell that it's sped up is by looking at the reflected pulse. When a wave goes into a medium where it's going to travel faster, very little wave energy gets reflected, and it gets reflected upright. Okay? It actually comes back the same direction that it went in. So if you had an up pulse, it comes back as an up pulse. Right? If it goes into a more dense medium where it travels slower, you actually get a lot of reflection and it comes back inverted. Right? So if I had a pulse going in that was up, it'll come back down. Right? That's how we can always tell whether the new medium is faster or slower. We look at the reflected pulse. If it comes back upright, it's faster. If it comes back inverted, it's slower. Those are just things you have to memorize. Okay, so this here slide is going to be important for you in terms of the things you need to know about these diagrams. I always have diagrams like this on the unit exam. Okay. All right, so the second situation here, we're going from the less dense or faster medium to the more dense or slower medium, and we can see that we have a reflected pulse that's coming back inverted, and we have a shorter, smaller wave. Okay, remember the amplitude goes down as well. Right? We've lost some wave energy there, okay? Because a lot of it got reflected. There's not as much wave energy going through into the new medium. Okay, all right. Okay, so if wave energy reflects from a more dense medium, okay, the reflected wave will come back inverted. All right, that's one of the things we have to memorize because I guarantee you, you'll get a diagram where that will be tested. Okay, reflection off of a less dense medium, okay, results in an upright wave. Okay, that is like from sound from water to air. It doesn't really matter on the example. Okay, we saw that on the springs here just a minute ago. Okay, so wave energy reflects from a more dense, it comes back inverted. Okay, so let's say I had just the slinky. Okay, so I have just the slinky, not the heavier coiled spring. Okay, and I make a wave in that, and it's not attached to anything. Will I get a wave come back to me? Or will the wave just go off the end of the slinky and disappear? Okay. Even though that slinky is not attached to anything, the energy in it has to go somewhere, right? So if I don't attach it to anything, that wave just goes into the air. So I'll get a reflected wave, but is the air going to be more or less dense than the spring? Less dense. So I'm going to get a very, very small upright reflected wave coming back to me. Right? Even though it's not attached to anything, it's still moving into another medium when it gets to the end of the slinky. All right, now I'm going to show you this one. This has to do with reflection. Okay, anybody play pool? Okay, anyone ever successfully pull off a bank shot in pool? Okay, so it's not just luck. Okay, and some people are good enough that they can kind of eyeball this, right? But something we need to know about both waves and particles is that when they reflect, the angle of incidence, that's the angle they come in at, is equal to the angle of reflection. It's called the law of reflection, right? You probably noticed this if you ever, took something shiny and then reflected the sun at someone's eyes. Okay, like sometimes you use like the face of your watch, right? And you shine and they get that. Okay, or your cell phone, in the face of your cell phone, you can reflect the sun off it into somebody's eyes. Okay, well, the angle of, you have to get that angle right? You have to go, okay, so the sun is there, and then I tilt this until, okay, but it's coming in, and the angle it comes in at is equal to the angle it goes off at. Right now, in pool, that's always true unless you really spin the ball. Okay, if you really spin the ball, then it can do something kind of funky off the bumper. Right, but if I want to pull this shot off, that is, hit the cue ball from here, okay, and hit this ball over here, what I want to do is make sure that this angle is the same. The easiest way to do that is this, not to guess. Okay, the bumper is like a mirror. You ever notice that when you stand in front of a mirror, your reflection is the same distance behind the mirror that you are in front? If you haven't noticed that, the next time you stand in the mirror, you will. It's something you can't unsee. Okay, your reflection will always be the same distance behind as you are in front. So what we would do when I was in university, because back when I was in university, you put coins in the pool table, okay, and you would only have to pay once if you were good, because then everyone else would pay for the next game to challenge you. Okay, being able to hit a bank shot is a big part of being able to continually run a table. So what we would do is we would sight along, okay, or we would kind of half measure how far it was from the ball to the bumper. Okay, then what we would do is we'd get our buddy to stand that far behind the bumper with his cue. And then we would use the cue as a sighter. Okay, so buddy would stand here. And then you would aim along a line that goes from the ball to your buddy. Okay, wherever that line intersects the bumper is where you need to aim for. And then it would bounce straight off the bumper and hit the ball every time. Okay, there's actually usually little markings along the bumpers that you can kind of use for that. And at the beginning of the night, most of the time, people would notice if you were doing this. By the end of the night, people didn't notice so much. Okay, but some people would get really angry if they saw you like sighting something up like this, but it works. Okay, you just imagine how far behind is it. Okay, sight along that spot and you'll make that shot every time, provided you don't spin the ball and you hit it square. Okay, by the end of the night, sometimes hitting the ball square becomes a little more difficult. Okay, for some reason, those fine motor skills start to deteriorate. Okay. All right, everyone follow how that one works? There you go. Now you can hit a bank shot in pool. It takes a little practice, but that's the physics behind it. You actually don't have to be that good a pool player in order to pull that off if you understand the law of reflection. Okay, I'm going to show you a couple of videos here on that now. Okay, when waves are transmitted, lots of things can change about them. We already said their speed can change, their wavelength can change, their direction can change. Okay, when their direction changes, we call that refraction. Right, so transmitted waves are always upright. So if I had a pulse coming in that was up, the transmitted wave will be up. The transmitted wave can never be different than the incident wave. All right, frequency remains the same because that's controlled by the source. Velocity will change because we're entering a new medium. Wavelength will change because it has to in response to the speed change. Amplitude can change, okay, from one to another because sometimes we lose some energy to reflection at the boundary. Okay, so amplitude can change. It's not a hard and fast rule or anything like that, but it generally does change as well. Right, and then the other thing that we don't have on here, okay, is that direction can also change. Okay, and that's if the wave comes in at an angle. Okay, obliquely means at an angle. Okay. Typically we draw, like if we have a whole bunch of waves, typically we represent them with a wave ray. Okay, that's just something you need to hear like once. It's not something we ever really work with until you get to physics 30, and then you'll start drawing wave ray diagrams and things like that. For us in physics 20, not all that important. Okay. So the normal line, okay, is this imaginary line that we draw at a right angle to the boundary. It helps us to measure the difference between the incoming and outgoing waves, or the incident and reflected or refracted waves. Right. So if I've got these waves coming in, okay, like this, I would draw a wave ray that shows their direction. Right. And then I could measure the angle between the normal and the waves, right? That would be my angle of incidence. And then I would draw another one, so my waves would, let's say, go off like this. Well, I didn't draw them very well, but let's say they're doing this, okay? I would be able to measure that angle. That would be the angle of reflection or refraction, sorry, in this case, refraction, because I've changed the direction of the wave. So the normal is just there as kind of a reference line, so we can see and measure if and how much the waves are changing direction, because how much they change direction tells us a lot about the differences between the two materials. Okay, so angle of incidence, angle of reflection, we talked about that. Those are always equal. Okay, so when a wave hits something that it can reflect off of, it bounces off at the same angle it came in at. All right, when a wave changes direction, that's refraction. Okay, we refract the wave, okay, and make it change the way that it's going. So the change in direction of a wave when it crosses the boundary between dissimilar media obliquely. So that's not head on. Okay, so that's what refraction is, and it looks like this. Right? Which one of these two media, the white or the green, is the slower one? The green. Okay, how do I know the green one's the slower one? Okay, it bends downwards, and look at the waves. Which waves are longer? Right? Like, are these waves closer together than these ones? Okay, so if they're closer together, they're shorter wavelength, slower speed, longer wavelength, higher speed. Right? Now, if we draw this normal line that they were talking about, okay, it's about right angle there. Okay, we can see that as these waves come in, they're going kind of they're going this direction, but the waves that are refracted are going this direction. In other words, they've bent towards the normal. Okay, their angle is smaller than that of the incident waves. If waves bend towards the normal, then they are slowing down. Okay, if we imagine that this was done the other way, okay, and that these waves are the incident waves, okay, we would draw them like this. Whoa. There we go. Okay, so we would have these waves going like this, and then these waves here, the ones that are in the faster medium, they go like this. They bend away from the normal. So when they speed up, they bend away. When they slow down, they bend towards the normal. That'll be super important next year when you talk about Snell's law. Okay, Snell's law is a crucial law that we talk about to do with light and waves and things like that. All right, so we'll watch a quick video here on refraction so you kind of see what that looks like as well. Okay, so if we're going from a fast medium to a slow medium, okay, then we see that in this case here, here's our angle of incidence. It's quite large. Here's our angle of refraction. It's quite small. It is bent towards the normal, okay, and we see that change in direction there. That's what's going on here, okay. Here would be our normal line, okay, and we can see that the light has bent towards the normal. This angle here is much bigger than this angle here is. Everyone all right with that? Okay, same idea I was talking about the spear fishing. Okay, this is where your eye tells you the fish is, but it's actually down here. Okay, because the light coming from it gets to the air where light travels faster, it bends away from the normal, goes to your eye, okay, giving you the illusion that the fish is actually straight away from you when it's not. Okay. All right, and then from slow to fast, the opposite happens, right? We have these waves here are close together. They go into the new medium. They bend away from the normal. They get wider, okay? The waves get longer. Okay, so when waves approach a more dense medium at an angle, the ray direction is not parallel, okay, and we see that their direction can change. Same is true here, okay? We've got waves coming in from the deep ocean, right? They're a certain distance apart, okay? There's really deep water over here, and then obviously quite shallow next to the shore, so the waves get turned as they encounter this peninsula that kind of sticks out, okay, kind of out into there, okay, they get turned because these part of the waves slow, okay, whereas these waves are still in the deep water, so they continue to go fast and they start to turn and wrap around and come into the cove. All right, this one I don't think is in your notes package, so you'll need to write down this stuff on diffraction, and then I will explain diffraction to you here in just a minute, okay? So just really what you need is just this sentence here and maybe a quick hand-drawn diagram of diffraction around an object and diffraction through a narrow slit. Okay, so just kind of make quick diagrams of those. All right, so diffraction is another behavior of waves, and diffraction is what happens when waves get around an object or when they get through a really narrow opening. Okay, waves do weird things when they encounter an object. Okay, and that is that they can, they obviously are slowed down and inhibited by it. Okay, but they can change their shape and still get around. Anytime they do that, we call them, we say that that is diffracting. Okay, so if I'm standing at a concert, but I'm behind a post, which would be like the worst seat in the house, but let's say that that happened, I could still hear everything. Okay, I mean, part of it would be reflections off the walls and things like that, but part of it is just that the waves will get around the object in front of me. They'll diffract around it. It's the same way that if someone's standing between me and somebody else, I can still hear what that person is saying. Okay, the waves just kind of slowly bend around that person. Does that mean they're not unaltered? No, they're definitely altered. Their shape changes a bit as they go around because they're slowed down, okay, and pushed, but they can do that. Okay, the other thing is that waves can diffract through a narrow opening. Okay, this happens all the time if the door is open in this room. All right, we can hear what's going on in the hallway. All right, if waves didn't diffract, the only people who would be able to hear what's going on in the hallway are people who are in a straight line with the door. Okay, everyone kind of follow me on that? Okay, it's the same reason why before we got doors on the bathrooms, we had real problems with hearing everything that went on in the bathroom. And I mean everything. Okay, that went on in the bathroom. All right, people would have conversations in there, and the conversations would come out through the door, diffract out the bathroom door, hit my door, and diffract. Okay, and they would make this semicircular wave pattern that would allow everybody in the classroom, including those on that wall, to hear what was being said in the bathroom. Sometimes we would rather not have heard things said in the bathroom. Okay, very socially awkward situation because then everyone would be watching to see who came out. Okay, after they hear certain things. Okay, so keep that in mind. If you're in the bathroom chatting, make sure the door is closed because I can hear everything in there. Okay, if my door is open and that door is open, it's really awkward. Okay, so stuff can diffract around. Now, this was crucial in proving that light was a wave because for the longest time, people thought it was not. People thought light was a particle, including Newton. Okay, lots of very respected scientists said, no, light is a particle because light doesn't do this. Okay, if light is a wave, then you shouldn't have what? A shadow, exactly. Okay, if light's a wave, then then you won't have a shadow. It would diffract around you and you wouldn't have a shadow. Okay, so for the longest time people said, look, it doesn't do that one thing. It does all the other stuff, we agree, but so do all particles. All particles reflect, all particles refract, but the one thing waves do that particles do not is diffract. Okay, and they had lots of evidence to show that light didn't do that. What they didn't understand was the nature of light. Light travels really, really fast and has an unimaginably short wavelength. Okay? As a result, it doesn't diffract very much over the distances that we can measure. Okay? It does diffract, but not a lot over the distances that we can measure. Okay? So what needed to be devised was a way to show that light was actually diffracting. Okay, and that it could bend. So what a guy named Thomas Youngs came up with was an experiment that's just like the two-speaker question we did yesterday, except he did it with light. Okay, he said if light diffracts, it'll do exactly what two speakers would do. Okay, if I have two sources of sound, okay, and they're both producing sound waves, okay, there are places where those sound waves overlap, right? And I would have a place where there's loud sound and a place where there's quiet sound, and so on and so on, right? I'd have the areas of constructive interference and destructive interference. He said, well, what I'm going to do is I'm going to set up an experiment like that with two light sources. Okay, and most people just looked at him and said, that's stupid. If you put two light bulbs in a room together, you don't get areas of shadow and light on the floor. Right? We talked about that yesterday as well. He said, well, no, I'm not going to do it that way. I'm going to make the slits that I use, I'm only going to use one light, and I'm going to make the slits really, really, really small because I think light has an incredibly small wavelength. And if I make the slits small enough, the wavelength will be, sorry, the slits will be close enough together that the wavelength will make this interference pattern. So what he had blown up really big, okay, is two slits that were really, really small. Okay, so these two slits. He had a light source back here, and he had a screen here. All right, actually he had a double slit, so he had one single slit behind this. All right, so he had his light source back here. Okay, and he said, I'm going to turn on this light, and then on this screen, I'm going to get patterns of light and dark. Okay, because essentially what will happen is I'll have these curved waves, okay, coming from each one of these light sources, and there'll be spots on the screen where waves will be overlapping its crests, waves are overlapping its crest and the trough, and I'll get patterns of light and dark. Everyone kind of follow his idea? All right, so what most people did is laughed at him and said, you're an idiot, because if you put a single slit in front of a light source, all you're going to get is a beam of light going through that light source, and that beam of light is going to hit this, and that'll be the end of your experiment. You're a tool, okay? But Young's had this figured out. He had these things very close together and the slits very close together as well, and when he turned on the light, he got exactly what he predicted. Patterns of light and dark on the screen, okay? Which proved light was a wave. The only way the light could have gotten through the second set of slits was if it diffracted through the first one. Okay? Otherwise, everyone else would have been right. Yeah, a beam of light shining on the back of that second barrier. Okay? So diffraction was proven by Young's double slit experiment. Now, we use this all the time, okay, in kind of modern day life here. Now, how many people have polarized sunglasses? Okay, if you have polarized sunglasses, the lenses of your glasses essentially have either a coating or built right into the glass, okay, what's called a diffraction grating that limits some of the light that's coming in, helps to reduce glare and things like that. Okay, anybody got cash? On some of our bills, if you have one of the older bills that has the maple leaf with the small hole in it, looks like it took a hole punch through it. Anyone got one of those? So I'm going to show you something really cool. I didn't bring one, but just check the wallet, see if you got one of those older bills. Okay, so it's an anti-counterfeiting measure, okay, that the Canadian Mint put into the bills. Okay, Adam, I'll get you to turn that off here. Okay, I'm also going to show you, this is kind of what Young's double slit experiment looked like. Okay, so I've got one beam here, but look how many dots are on the board. Okay, so it's diffracting the light to those spots. The dots would be areas of constructive interference, and destructive interference would be the dark spots in between. Okay, you can see there. I get a whole bunch of them. Okay, there I get less. Okay, see how they're getting closer and closer together? Right. Did anyone find a bill that had that on it? Okay, if you do, try it at home. Just get a cheap, these are just dollar store laser pointers, they're like $1.25. Okay, but through that little hole in the maple leaf, if you shine this through, you'll get a pattern. Okay, and it'll have dollar signs. You have one? Okay. Oh, perfect. Okay, so it'll have dollar signs, and then it'll also have the denomination in there. Okay. This is important to remember. If you ever sell anything on like Kijiji or Craigslist or anything like that, okay, this is how you check to make sure someone isn't giving you counterfeit bills. Okay, let's get a little closer here. Okay, do you see the dollar sign and the 5? if I get further away, it just gets too blurry. Yeah. It's just meant to be tested on like a sheet of paper, really up close. Okay. See the 5 and the $sign there? Okay. So they've built in a diffraction grating into the money. Okay. So you can test it. Right. Like I did this when I sold a truck a few years ago, and the guy paid me in cash. So I had like all these hundreds and stuff. I'm like, yeah. And I knew he was coming with cash, so I brought one of the school's laser pointers. Okay, and I just pulled bills at random from the stack that he gave me, and I did that with him, and I checked him, and he had no idea what I was doing. And he's like, "What are you doing?" I'm like, "Well, it's not that I don't trust you, but I don't know you, okay? And this is a lot of money, so I want to check and make sure that none of these are counterfeit." He's like, "Well, I just went to the bank and got them." I'm like, "Oh, that's fine. I'm just checking. Like, don't take it personally." You know, and so I checked a few of them. He's, well, how do you know what you're doing? I said, well, there's a diffraction grating in the money, and you just shine a laser through that, and it shows up. If it's fake, it won't work. Okay? It's almost impossible to manufacture that, okay, anywhere other than the mint. So that's in some of your money. The newer money, I think, has it in one place, but I haven't found it exactly yet. It's supposed to have something like that in one of the plastic parts of the money. Okay, so there you go. If you ever sell something on Kijiji, okay, and you want to double check that someone's not ripping you off with counterfeit money, okay, that's a way to do it. All right, Adam, I'll get you to turn that back on for me, please. Okay, so what do we got here? We got a few minutes left in class. You know what? I will let you have the last 10 minutes here to talk to your group with your West Ed assignment. Okay. Tomorrow we're going to be working on some wave behavior stuff before I move on and introduce the Doppler effect. All right, so you got a few minutes here to work with your group on your West Ed assignment. Take advantage.